Hello, I'm the massive Mr. Daycock, and today I am going to be teaching you how to solve recurrence relations when the auxiliary equation has repeated roots. So here is an example. First of all, we're going to do what we usually do, and we're going to rearrange it so it's equal to 0. We're going to get un is equal to un minus 4 un minus 1 plus 4 un minus 2 equals 0. And now we can just rewrite it into our auxiliary equation. This is the highest factor of n, or highest value of n here. So we're going to write this as our r squared minus 4 lots of our second highest r plus 4 lots of our lowest, and that's just going to be our constant term. And that's going to equal 0. So now, solving this, it factorizes nicely r minus 2 times by r minus 2, which is r minus 2 squared equal to 0. And so we get r equals 2 as a repeated root. Okay, now what happens here? Well, as we were saying before, this gives us two possibilities. We've got un is equal to a times 2 to the power of n, or un is equal to b times by 2 to the power of n, except these are effectively the same. And if I were to take the sum of these two solutions, these two different solutions, then what we would get is a situation where they would just sum to one solution. And so we're going to do exactly the same thing we did when we had two possibilities between the complementary function and the particular solution, and we're just going to multiply the second one by n. So we're going to write this second one, our second option, as b lots of n times by 2 to the n. And that's all there is to it. If you ever get one part of your solution being a repeat of another part of your solution, so the constants would just add, then just multiply one of them by n and you get your new possibility. And so we're going to look at this as un equal to a lots of 2 to the power of n plus b n lots of 2 to the power of n. And now we can just solve it nice and easily, not too difficult. We pick n equals 1, go back to our initial conditions. That gives us un is u1 is 3, so we get 3 is equal to a times by 2 to the power of 1 plus b times by 1 times by 2 to the power of 1, and we're going to end up with 3 equal to 2a plus 2b. And then we're going to try n equals 2. Going back to the top, we can see that u2 is 4, and so we're going to get 4 is equal to a multiplied by 2 to the power of 2, because remember our n is 2, plus b times by 2 times by 2 to the power of 2. And that gives us 4 is equal to 4a plus 8b, and be careful about that. Now here I've got one equation and another equation with two unknowns. This is simultaneous equations. Call that equation 1, we'll call that equation 2. And what I want to do is I want to multiply equation 1 by 2, and we get 6 equals 4a plus 4b, and then I'm going to subtract these equations. And 6 equal to 4a plus 4b, subtract 4 equal to 4a plus 8b, and we're going to get 2 is equal to negative 4b. And so b is equal to negative 1/2. Substituting that back in, so I'm going to substitute this back into this original equation here, and we're going to end up with 3 equal to 2a. 2 times negative 1/2 is minus 1, so 2a equals 4 and a equals 2. And so that gives us our final solution, ours, un equal to, plugging A and B back into this, or actually not back into there, plugging A and B back into here, that gives us our final solution of un is equal to A is 2 lots of 2 to the n, and then B is minus a half, minus 1/2 times n times by 2 to the n. And that is our final solution. We can actually do a little bit of simplifying by putting the 2's together, and that gives us 2 to the power of n plus 1 minus, and a half is 2 to the power of negative 1, n times by 2 to the power of n minus 1. And that arguably is more simple. Okay, on to a second example, which is up here somewhere. There we are. Solve the recurrence relation un is equal to negative 6 un minus 1 minus 9 un minus 2, with u1 equal to negative 1 and u2 equal to negative 2. So, again, rearrange un is equal to, not equal to, un plus 6 lots of un minus 1 plus 9 lots of un minus 2 is equal to 0. We're going to solve, therefore, r squared plus 6r plus 9 equals 0, and we get r plus 3 squared equals 0, or r equals negative 3. And so our general solution that we're going to try is going to be un equal to a lots of negative 3 to the n plus b lots of n times by negative 3 to the n. And notice this extra n in here in the second one to account for that repeated root and still give us the two terms that we need. Then at this point, as always, we're going to go back to our initial conditions and say we have, when n equals 1, we've got u1 is negative 1, so we get negative 1 equal to a times by negative 3 to the 1 plus b times by 1 times by negative 3 to the power of 1. And that gives us negative 1 is equal to negative 3a minus 3b. And then we want to plug in n equals 2, and we're going to get negative 2, because if we go back up to the top, we can see that u2 is negative 2. Negative 2 is equal to a lots of negative 3 to the power of 2, because remember we were plugging in n equals 2, plus b times by 2 times by negative 3 to the power of 2. And that gives us negative 2 is equal to 9a plus 18b. And notice these are now positive, because when we square a negative, we do indeed get a positive. And so what I'm going to do, I'm going to multiply, call this here equation 1, call this here equation 2, and I'm going to multiply equation 1 by 3 to make them match up. And I get negative 3 is equal to negative 9a minus 9b. Add these together because I want the a's to cancel, and I get negative 5 is equal to the a's cancel, and I get 9b. And that gives us b is equal to negative 5/9. Plugging that back in, as always, plugging that back into here, and we're going to get negative 1 is equal to negative 3a plus, because negative times negative is positive, 15/9. Subtracting those 15/9, we're going to end up with, so this is already negative 9/9, we're going to subtract another 15, we're going to end up with negative 24/9 is equal to minus 3a. Divide that by minus 3, 24 divided by 3 is 8, and we get a is equal to positive, because a negative divided by negative is a positive, 8/9. And therefore our general solution is un is equal to 8/9 of negative 3 to the n, and b is negative minus 5/9 of n times by negative 3 to the n. And as before, 9 is actually 1 over 9 is negative 3 to the power of negative 2, and we could in fact write this as un equals 8 times by negative 3 to the negative 2, negative 3 to the n, minus 5 lots of negative 3 to the negative 2, n, negative 3 to the n, and then combine those negative 3's, we get 8 lots of negative 3 to the n minus 2, minus 5n lots of negative 3 to the n minus 2. And we're done. And so, as you can see, if you have repeated roots, it is a very, very similar situation. Pretty much everything still works out the same, except you have to account for the fact the two terms have the same coefficients here, and you account for that by including this n here. Okay, thank you for watching, and next time we're going to be looking at an even more complicated situation where the auxiliary equation has complex roots, i.e. it has no real solutions. Okay, thank you for watching. See you in the next video.